a quiet archive record, the wow signal. The following account concerns a single unexplained radio transmission detected in 1977 by a university radio telescope in Ohio. A signal that appeared exactly once, matched every expectation scientists had for an artificial source, and then vanished forever. It was not a sighting, not a photograph, not a story passed from person to person, but a line of data printed on continuous paper. Decades later, it remains the strongest unresolved candidate for a signal from an intelligent source beyond Earth. This is its story. Chapter 1: A telescope that waited. The telescope was not built to listen for voices. It was built to listen for structure. When the Ohio State University Radio Observatory began taking shape in the late 1950s, the ambition behind it was practical, not philosophical. Radio astronomy was still young. The universe, when viewed through radio frequencies, was largely unmapped. What existed were isolated observations, bright sources here, strange emissions there, but no comprehensive picture. The man responsible for the observatory, John Krause, understood something fundamental. If astronomy was to progress beyond isolated discoveries, it needed surveys, long, methodical sweeps of the sky, data gathered patiently, without expectation. The structure that emerged from that thinking was unconventional. It did not resemble the iconic, bowl-shaped dishes that most people associate with radio telescopes. Instead, it stretched horizontally across farmland, flat, expansive, and immobile. Aluminum mesh covered the ground like a metallic field. At one end stood a parabolic reflector, tall and curved. At the other, a tilting flat reflector, adjustable only in elevation. The telescope could not turn left or right. It did not track objects. It relied entirely on the rotation of the Earth. As the planet turned, the sky drifted overhead. The telescope listened to whatever passed through its beam, day after day, night after night. This design was not a compromise, it was a choice. By eliminating mechanical complexity, the telescope achieved something rare: stability, predictability. A well-defined beam shape that behaved exactly as mathematics said it should. It was named Big Ear, partly in jest, partly in recognition of its singular purpose: to listen. For more than a decade after it became operational in the early 1960s, Big Ear did exactly what it was designed to do. It conducted the Ohio All-Sky Survey, cataloging tens of thousands of radio sources. Quasars, then newly discovered and poorly understood, appeared in its data. Distant galaxies revealed themselves not as points of light, but as complex radio structures. The telescope helped reshape humanity's understanding of the universe. And then, quietly, funding ended. By the early 1970s, astronomy had shifted. Larger, steerable dishes were being built elsewhere. Budgets followed novelty. The National Science Foundation ended support for Big Ear's primary mission. The telescope stood finished, functional, and without a purpose. It was at this point that a smaller idea took hold. Not a grand initiative, not a national program, just a question. What if, instead of listening broadly, the telescope listened carefully? The search for extraterrestrial intelligence, SETI, was not fringe science by the 1970s, but it was not mainstream either. It occupied a narrow space, respected enough to be discussed seriously, but speculative enough to make funding uncertain. The logic behind it was straightforward. Radio waves travel vast distances with relatively little loss. Technology capable of producing radio signals is achievable well before interstellar travel. If another civilization existed and wished to be noticed, radio transmission was an efficient method. But not just any radio signal. Nature produces radio noise constantly. Stars emit it, gas clouds emit it, even planets can emit it. These signals are typically broad in frequency, spread out, messy, statistically random. Technology, by contrast, favors efficiency. Narrowband signals, confined to extremely small frequency ranges, are efficient, precise, and rare in nature. They stand out. If intelligence wished to announce itself, narrowband radio would be an obvious choice. This was the premise, and Big Ear, though aging, was well suited to test it. The SETI program at Ohio State began modestly in 1973. There was no dedicated funding, no staff assigned full-time. The system was adapted quietly, using volunteer labor and existing infrastructure. A new receiver was installed, optimized to monitor 50 narrow-frequency channels simultaneously. Each channel was watched continuously. The telescope listened without bias. The data flowed into a computer whose limitations were severe, even by the standards of the time. Memory was scarce, processing power minimal. Everything was designed for efficiency. Every 10 seconds, the system sampled each channel and recorded a single character representing signal strength. Weak signals became numbers. Stronger ones became letters. The output was printed. Paper did not forget. Paper could be reviewed. Paper could be archived. The decision to rely on printouts rather than real-time displays would later prove crucial. By 1977, the system had been running for several years. Nothing extraordinary had appeared. This did not trouble the people involved. SETI was understood as a long endeavor. Silence was expected. In fact, silence was the default assumption. The absence of signals did not imply failure. It implied patience. The telescope listened through seasons, through weather, through changes in staff and schedules. The Earth turned, the sky passed overhead, and then came August. On August 15th, 1977, Big Ear was set to an elevation corresponding to a region of sky near the constellation Sagittarius. This area lies close to the galactic plane, a dense band of stars, gas, and dust that forms the disk of the Milky Way. It was a reasonable place to listen. The flat reflector was angled. The parabolic wall weighted. The feed horns were aligned. The receivers were active. No adjustments were made that night. Nothing was unusual. As the Earth rotated, radio waves from deep space arrived at the telescope, bounced off the reflectors, and converged into the horns. They were converted into electrical signals, processed, and reduced to symbols on paper. Most of those symbols were unremarkable. Then, in one channel, something changed. At a frequency close to 1420 megahertz, the background noise rose. Not abruptly, gradually. 10 seconds passed. It rose again. Another 10 seconds. Higher still. The signal continued to increase, passing levels rarely seen in years of observation. The computer translated the intensity into characters. 6, 0, Q, U, J, At its peak, the signal was roughly 30 times stronger than the surrounding background noise. This was not borderline. This was unmistakable. Then, as smoothly as it had risen, the signal declined. J became 5. 5 became lower values. Within 72 seconds, the channel returned to normal. The event was over. No alarms sounded. No one marked the time. The telescope continued its sweep. The second feed horn, offset slightly in time, never saw the signal. This detail would later become central, but at the moment it happened, nothing reacted. Because no one was watching. 2 days later, the paper arrived. Jerry Amon had volunteered to review the printouts because he enjoyed the work. There was no glamour in it, just pages and pages of numbers and letters, each representing 10 seconds of the universe's radio output. He knew the patterns. Noise was familiar. Interference was familiar. This was neither. The sequence stood out immediately, not because it was dramatic, but because it was orderly, structured, predictable. It looked right. Amon paused. He reread the line. He checked the channel number. He scanned adjacent channels. Nothing else behaved similarly. With a red pen, he circled the characters. He wrote "wow" in the margin, not as a conclusion, as a reaction. What followed was not excitement, but restraint. Amon contacted John Krause. Krause contacted Bob Dixon. Together, they examined the data carefully. They did not announce anything. They did not speculate publicly. They did what scientists are trained to do. They tried to make it go away. They checked the system. No errors, no malfunctions. They examined the timestamps. They checked other channels. Nothing correlated. They considered terrestrial interference. But interference does not behave this way. It does not rise and fall smoothly with the rotation of the Earth. It does not remain confined to a single narrow frequency. It does not respect protected bands. They considered satellites. But satellites move differently across the sky. They do not mimic the apparent motion of distant stars. They considered natural sources. But no known astrophysical process produces a narrowband signal that turns on once and never repeats. They returned to the feed horns. The signal had appeared in only one. That meant one of two things. Either the signal was not extraterrestrial, or it was, and it stopped transmitting at exactly the wrong moment. Neither explanation was comfortable. The telescope was pointed back, again and again, for days, for weeks, for months. The signal never returned. Silence resumed, but the silence was different now, because something had broken it once. The night of August 15th did not provide answers. It provided a boundary, a moment where the universe behaved in a way that fit expectation, but refused confirmation. The telescope did not prove intelligence existed elsewhere. It did something more subtle. It demonstrated that the search was not empty, that something, somewhere, could produce a signal that matched our predictions exactly, and then vanish, leaving behind nothing but paper, and a word written in red ink. Wow. Chapter 2, The Shape of a Real Signal. In science, discovery is not announced. It is resisted. The first response to anything extraordinary is not belief, but suspicion. directed not outward, but inward, toward instruments, toward assumptions, toward the quiet, ever-present possibility of error. John Krauss understood this instinctively. He had built Big Ear not to prove ideas, but to remove doubt. Every design choice, the fixed structure, the reliance on Earth's rotation, the dual feed horns, had been made to ensure that when something appeared in the data, it could be tested against expectation. And so when Jerry Amon brought the circle printout to him, Krauss did not ask what it meant. He asked whether it was real. The first days after the discovery of the WOW signal were methodical and restrained. There were no press releases, no outside consultations. The event was treated as a technical anomaly until proven otherwise. The printout was examined again and again. The timestamps were checked, the channel numbers verified, the intensity values recalculated by hand. Nothing changed. The signal's defining feature, its smooth rise and fall over exactly 72 seconds, was not an interpretation. It was a direct reflection of the telescope's beam pattern. Big Ear's response to a point source in the sky was well understood. The beam had a known width. As Earth rotated, a fixed source would enter the beam, peak at center, and exit. That was precisely what the data showed. If the signal had come from a distant star, galaxy, or transmitter moving with the cosmic background, this was exactly how it would appear. That fact alone made it troubling. The next step was to eliminate local interference. Radio astronomers live with interference. It is their constant adversary. Aircraft radar, communication systems, satellites, even poorly shielded electronics on Earth can contaminate observations. Over time, experienced researchers develop an instinct for what interference looks like. The WOW signal did not look like interference. Interference tends to behave erratically. It switches on and off abruptly. It jumps frequencies. It appears in multiple channels at once. It often shows irregular intensity patterns, spikes, dropouts, distortions. The WOW signal did none of these things. It appeared in only one frequency channel. It rose smoothly. It fell smoothly. And it stayed exactly where it was. That alone narrowed the field dramatically. Attention then turned to frequency. The signal appeared near 1,420 megahertz, the hydrogen line. This frequency is protected internationally. It is reserved for scientific research. No licensed transmitter is allowed to operate there. This does not mean transmissions never occur illegally, but it does mean that routine interference is unlikely. Any source transmitting there would have to do so deliberately, knowingly violating international agreements. Even more importantly, terrestrial transmitters do not remain fixed relative to the stars. Their apparent motion across the sky is different. Big Ear's design allowed astronomers to infer motion from timing alone. The WOW signal moved like the stars. That was not a small detail. Satellites were considered next. By 1977, Earth-orbiting satellites were common, and some transmitted radio signals, but satellites move rapidly relative to the Earth's surface. Their apparent motion through the sky is fast and directional. They do not linger in a telescope's beam for over a minute while maintaining a steady intensity profile. For a satellite to produce the WOW signal, it would have needed to transmit at a forbidden frequency, move at exactly the same apparent rate as a distant cosmic source, and turn off at precisely the moment required to avoid detection by Big Ear's second feed horn. That combination strained plausibility. Krauss and Dixon checked satellite catalogs anyway. None matched. The second feed horn became the focal point. Big Ear's twin horns were positioned so that any signal from a fixed celestial source would appear twice, once in each horn, separated by a few minutes as Earth rotated. The WOW signal appeared in only one. This fact was both tantalizing and frustrating. If the signal were real and extraterrestrial, it implied that the transmitter was not continuous. It had turned off or changed frequency within minutes. If the signal were terrestrial, it raised questions about why it would mimic celestial motion so precisely. Neither explanation was comfortable, and neither could be proven. For the next several weeks, the observatory adjusted its listening strategy. The telescope was returned to the same elevation. The same patch of sky was allowed to pass through the beam night after night. The receivers were monitored carefully. Printouts accumulated. Nothing appeared. The silence was not dramatic. It was ordinary. The kind of silence astronomers were used to. But now it carried weight, because it followed something unmistakable. The team resisted the temptation to speculate. They did not frame the signal as extraterrestrial. They did not frame it as proof of anything. Internally, it was referred to simply as an unidentified narrowband event. But privately, each person involved understood the implications. The signal had behaved exactly as SETI researchers had predicted an artificial signal would behave. Except for one thing, it did not repeat. The lack of repetition became the defining problem. Science relies on verification. Reproducibility is not optional. It is foundational. A phenomenon observed once cannot be confirmed, only noted. This was not ignorance. This was discipline. Krauss insisted that without repetition, the signal could not be claimed as evidence of intelligence. It could not even be claimed as extraterrestrial. It remained unresolved. But unresolved did not mean insignificant. Over time, the internal discussions expanded. Could the signal have come from a natural but unknown astrophysical process? Possibly, but no known mechanism produced narrowband emissions like this. Could it have been a reflection or amplification of an Earth-based signal? The beam pattern argued against it. Could it have been an intentional transmission aimed briefly in Earth's direction? This possibility was unsettling because it could not be tested. If a distant civilization used a directional beam rather than a continuous beacon, the odds of catching it would be low. It might sweep past Earth only occasionally, once, perhaps, in decades. That idea could not be proven, nor could it be dismissed. Years passed. Other SETI programs emerged. New telescopes with greater sensitivity scanned the sky. Computers improved. Data storage became digital. Follow-up searches were conducted near the WOW signal's frequency and sky location. Nothing. The silence persisted. Within the scientific community, the WOW signal became a cautionary case. It was cited carefully, always with caveats. It was never presented as proof, but it was not ignored either. It occupied a narrow category of its own, a signal that matched expectations, a signal that resisted explanation, a signal that could not be confirmed. It became a reminder of the limits of observation. For those who had been closest to it, The experience was not one of disappointment, but of humility. The universe had spoken once, or appeared to, and then it had returned to silence. Not with hostility, not with indifference, just with distance. As the years moved on, Big Ear itself began to fade from prominence. New instruments took its place. Funding priorities shifted again. The telescope remained operational, but its role diminished. Yet the paper remained. The printout with the red circle, the word written in ink, a human reaction preserved alongside machine data. The shape of the signal was known. Its origin was not. And between those two facts lay the heart of the mystery, not an answer, but a boundary, a reminder that even when the universe behaves exactly as expected, it is not obligated to explain itself. The search would continue, but the wow signal would never be heard again. Chapter 3: The Years of Listening. The most difficult part of a mystery is not the moment it appears. It is the time that follows. After the wow signal, there was no dramatic escalation, no sudden influx of funding, no emergency meetings of global institutions, no headlines announcing a turning point in human history. No government delegations arrived at the observatory. No outside authority seized the data. No one declared that history had changed. Instead, what followed was something quieter, slower, and far more demanding. Waiting, listening, and accepting that whatever had happened on that August night had left behind no instructions on how to proceed. The Big Ear had done exactly what it was designed to do. It had detected an anomaly, recorded it faithfully, and moved on. It did not interpret. It did not speculate. It did not linger. Those burdens fell entirely on the people who read the paper afterward. And paper was all they had. In the weeks immediately following the discovery, the response from the Ohio State Radio Observatory was disciplined and conservative. There was no attempt to chase the signal emotionally, no rush to reinterpret its meaning. Instead, the telescope was returned again and again to the same elevation. The same slice of sky was allowed to drift overhead as Earth rotated beneath it. The geometry mattered. The timing mattered. Everything that could be repeated was. Night after night, the receivers listened. Nothing returned. At first, this absence was not alarming. SETI researchers never expected signals to be frequent. In fact, most theoretical models assumed the opposite. If intelligent civilizations existed at all, their transmissions, if intentional, might be rare, brief, or tightly focused. Even an Earth-like civilization does not broadcast continuously into space without purpose. Our own most powerful transmissions are directional, transient, and often unintentional. Silence, therefore, was not unexpected. But this silence was different, because the wow signal had not behaved like noise. Ordinary radio interference announces itself through chaos. It appears suddenly. It jumps frequencies. It fluctuates unpredictably. It contaminates multiple channels. It rarely respects the shape of a telescope's beam or the rhythm of Earth's rotation. The wow signal had done none of that. It had risen smoothly. It had peaked cleanly. It had faded exactly as expected. And then it had vanished. This was the unsettling part. Not that the signal failed to return, but that it had arrived so precisely in the first place. As weeks turned into months, the search broadened slightly but cautiously. Nearby frequencies were monitored in case the signal had drifted. Adjacent sky regions were examined in case the source was not perfectly stationary or had been mislocalized. Follow-up scans were scheduled whenever the telescope's limited flexibility allowed. The logic was straightforward. If the signal was real and astrophysical, perhaps it would appear again under slightly different conditions. If it was artificial, perhaps it would recur intermittently. Nothing did. The telescope continued its routine work, cataloging ordinary cosmic sources, pulsars, quasars, radio galaxies, while the extraordinary remained stubbornly absent. And slowly, an uncomfortable reality set in. Whatever had happened might never happen again. Within the small SETI community, news of the signal spread cautiously and unevenly. It was discussed in internal reports, mentioned in conference presentations, and eventually described in publications, but always with restraint. Language was careful. Claims were narrow. Conclusions were avoided. No one wanted to overstate what could not be confirmed. The signal was real. Its origin was not known. That was all that could be said with certainty. Anything more would have crossed the boundary between observation and belief. For some researchers, this restraint was deeply frustrating. Science is built on repetition. Experiments are designed so that phenomena can be observed again and again, tested under different conditions, verified independently, and challenged by competing interpretations. The WOW signal resisted all of that. It could not be reproduced. It could not be interrogated. It could not be advanced beyond where it already stood. It existed as a single event, a solitary data point, a measurement without a pattern. In many branches of science, such an observation would quietly disappear, noted briefly and then set aside. But SETI was different. It was not searching for a known phenomenon under controlled conditions. It was searching for something that might only appear once. And that changed how singularity was interpreted. Paradoxically, the fact that the WOW signal stood alone made it more compelling, not less. Had the signal been weak, it might have been dismissed as statistical noise. Had it repeated frequently, it might have been identified and explained. Instead, it occupied an uncomfortable middle ground. Strong, clean, and fleeting. It was powerful enough to command attention, but elusive enough to deny resolution. It refused to settle into either category. As years passed, other researchers began to take interest, often independently and often from different disciplinary angles. Some approached the problem analytically, asking whether any known natural sources could plausibly generate a narrowband emission of such intensity at that frequency. Astrophysical mazes were considered, but their spectral characteristics did not match. Thermal emissions were ruled out. Known stellar processes failed to account for the signal's precision. Others explored the possibility of reflections, signals originating on Earth, bouncing off space debris, satellites, or distant objects, and returning altered in ways that mimicked a celestial source. Models were proposed, simulated, and tested. One by one, they failed. The geometry did not work. The timing did not align. The beam pattern did not fit. Reflections did not rise and fall smoothly with Earth's rotation. They did not respect protected frequency bands. They did not behave as the WOW signal had behaved. A different line of inquiry considered the possibility of comets or diffuse hydrogen clouds emitting briefly at the hydrogen line. Decades later, this idea would be revisited with improved cometry data, but at the time, it remained speculative. There was no direct evidence that such objects could produce a signal of the observed strength and stability, nor that they would do so for precisely 72 seconds and then stop. Once again, the problem was the same. There was nothing to compare it to. No second event, no control case, no confirming observation. The WOW signal existed in isolation, immune to statistical reinforcement. Meanwhile, the broader search for extraterrestrial intelligence continued elsewhere. New facilities came online. Larger radio telescopes with steerable dishes replaced fixed instruments like Big Ear. Receiver technology improved rapidly. Computers capable of processing enormous datasets replaced paper printouts and human pattern recognition. SETI experiments began scanning wider bandwidths, monitoring millions and eventually billions of frequency channels simultaneously. The search grew broader, faster, and more automated. Yet despite these advances, the fundamental challenge remained unchanged. SETI was not like other sciences. It did not test hypotheses in the traditional sense. It did not manipulate variables. It did not provoke responses. It listened, and listening does not guarantee response. Some scientists quietly distanced themselves from the WOW signal, not because it had been disproven, but because it was unresolved. Academic careers are built on progress, on results that lead somewhere concrete. A mystery that cannot be advanced, replicated, or closed is difficult to carry forward professionally. There was no shame in stepping away. Others, however, remained quietly fascinated. They understood that even if the signal were ultimately mundane, it represented the exact kind of anomaly SETI was designed to detect. If nothing else, it demonstrated that the search was sensitive enough to notice something genuinely unusual, and disciplined enough not to overinterpret it. In that sense, the WOW signal validated the methodology, even as it defied explanation. Public awareness of the signal grew slowly, largely through secondary retellings rather than official announcements. It acquired a kind of legend, not through exaggeration, but through persistence. The circled printout, the handwritten wow, the fact that the discovery came from a university telescope rather than a classified military system. It felt human, not in its origin, but in its discovery. A quiet evening, a kitchen table, a pen, a word written in surprise. These details anchored the story in something recognizable, something grounded, even as the implications stretched outward into cosmic uncertainty. As the 1980s approached, the Big Ear itself faced mounting uncertainty. Funding pressures intensified. The telescope's design, once innovative and economical, was now technically limiting. It could not track targets. It could not follow up immediately. It could not adapt quickly to new search strategies. Still, it continued to listen, and occasionally, out of discipline, habit, or hope, it was pointed again toward the coordinates of the WOW signal. Still nothing. This prolonged absence forced SETI researchers to confront an uncomfortable truth. Even if the signal were extraterrestrial, it might be effectively impossible to prove. a civilization transmitting intermittently or using highly directional beams could pass unnoticed most of the time. The vastness of space ensured that coincidence played a dominant role. Detection might depend on alignment, timing, and chance, rather than persistence. The wow signal might not have been a message intended for Earth. It might have been a crossing of paths. This realization reshaped how some scientists thought about the search itself. Perhaps the universe was not silent. Perhaps it was simply speaking rarely. And perhaps humanity had only just learned how to listen well enough to notice. By the time the Big Ear was dismantled in the late 1990s, the wow signal had already taken on its enduring form, not as an answer, but as a benchmark. It became the standard against which future candidate signals were measured. Was it narrowband? Was it strong? Did it follow celestial motion? If not, it was something else. And yet, no subsequent detection ever matched it exactly. There were candidates, there were false alarms, there were moments of excitement followed by explanation, but none carried the same unresolved weight. The years of listening taught a difficult lesson. Discovery does not always arrive with clarity. Sometimes it arrives as a question that refuses to go away, and sometimes the most profound outcome of listening is learning how much patience the universe requires. The wow signal did not end the search. It deepened it, because once you know that something like that can happen, even once, you cannot listen the same way again. Chapter 4. When the instrument fell silent. Long before the signal became a mystery, the telescope itself had become a compromise. Big Ear was never meant to be permanent. It was conceived during a period when ambition routinely exceeded available funding, when scientific ingenuity was expected to compensate for scarcity, and when universities relied heavily on the labor of graduate students and volunteers to realize projects of national importance. Its vast aluminum surfaces, fixed geometry, and reliance on Earth's rotation were not shortcomings at the time. They were solutions, elegant, economical, and effective for a specific scientific moment. That moment passed. By the late 1980s, radio astronomy had changed in ways Big Ear could not adapt to. New dishes could steer electronically across the sky, track targets in real time, and respond instantly to unexpected detections. Interferometric arrays synthesized apertures far larger than any single structure, while receivers sampled millions of frequencies simultaneously with precision unimaginable when Big Ear was designed. Compared to these instruments, Big Ear was rigid. It could not pivot toward a transient event. It could not linger on a promising source. It could only wait. Still, it listened. Even as funding dwindled and its role narrowed, the telescope continued operating. The SETI program at Ohio State survived largely through dedication rather than support, through people willing to read endless computer printouts, maintain aging electronics, and justify a search whose success could not be guaranteed or scheduled. It was not a program driven by milestones or deliverables. It persisted because those involved believed that some questions were worth asking, even when answers might never arrive. It was not a glamorous endeavor. It was a faithful one. The land beneath Big Ear had always been borrowed. From its earliest days, the observatory existed on property owned by Ohio Wesleyan University, not Ohio State. This arrangement worked for decades because the telescope's presence aligned with broader priorities: scientific research, educational prestige, and national investment in fundamental science. The land had little competing value when the telescope was built. It was quiet, rural, and largely unused. But priorities change. By the 1990s, the surrounding area had grown. Roads expanded. Housing developments crept closer. What had once been farmland became desirable real estate. The land itself, flat, cleared, and accessible, acquired a value unrelated to astronomy. The telescope, by contrast, produced no revenue. It attracted no tourists. It offered no direct economic return. A golf course could. The decision to sell the land did not emerge from scientific debate or institutional reflection. It arrived as a notice. For those who had spent their professional lives working with Big Ear, the news felt abrupt, almost unreal. There was no dramatic confrontation, no prolonged public dispute that halted the process. The sale proceeded quietly, efficiently, with the logic of economics overriding the weight of scientific legacy. John Krauss was already in his 90s when he learned that the telescope he had designed, defended, and built over years of effort would be dismantled. He had seen technologies come and go. He understood that instruments age. But this loss struck differently. He described the day as one of infamy, not because Big Ear was flawless or irreplaceable, but because it had not finished asking its questions. The dismantling itself was not ceremonial. There were no speeches marking the end of an era, no formal recognition of what the telescope had contributed. Piece by piece, the aluminum reflectors were removed. The parabolic wall was dismantled. The feed horns, those twin funnels that had once captured the wow signal, were taken away and stored or discarded. The ground plane was cleared. Where radio waves had once slid silently across metal, grass was planted. The sky remained. The ear that listened to it did not. For many connected to the observatory, the loss felt like a kind of erasure. Big Ear had not only discovered the wow signal, it had mapped the radio sky, catalogued thousands of previously unknown sources, and trained generations of students in the discipline of observation. It was a place where curiosity had been institutionalized, where looking without immediate payoff was considered a legitimate scientific act. Its removal symbolized a shift from patience to productivity, from open-ended exploration to targeted outcomes. In that sense, the telescope's end mirrored the broader challenge facing SETI itself. The search for extraterrestrial intelligence was, by definition, open-ended. It could not promise results on a funding cycle. It asked for tolerance of uncertainty in an era increasingly intolerant of it. The wow signal, meanwhile, outlived the structure that detected it. The data was archived, the printout preserved, the story continued to circulate, passed from scientist to scientist, from academic footnotes to documentaries and lectures. In some retellings, the signal was exaggerated, framed as near proof of extraterrestrial contact. In others, it was minimized, dismissed as an anomaly unworthy of continued attention. But the core facts never changed. A signal appeared. It matched expectations. It did not repeat. And now, the instrument that might have caught it again was gone. This absence sharpened the signal's significance. Had Big Ear remained operational, perhaps it would have heard something else, something similar, something clarifying. Or perhaps it would have heard nothing, reinforcing the silence. There was no way to know. The opportunity had passed, and with it, the possibility of direct continuity. Within the scientific community, reactions to the dismantling were mixed. Some accepted it as inevitable. Instruments age, technologies advance, resources are finite. Science, they argued, is not sentimentality. Others felt something important had been lost, not merely a telescope, but a way of doing science that tolerated ambiguity and rewarded patience. Big Ear had not been optimized for efficiency. It had been optimized for listening. The site itself changed quickly. Fairways replaced foundations. Homes rose where support structures once stood. For new residents, there was little indication that the land had ever hosted one of the most unusual scientific instruments of the 20th century. Only a few markers remained, and the memory, preserved mainly by those who knew what had once stood there. As SETI efforts migrated to other facilities, the WOW signal became untethered from place. It was no longer something that belonged to Ohio or to Big Ear, or even to a specific group of scientists. It belonged to the archive, to the category of unanswered observations that science carries forward, not as failures, but as reminders. There was a quiet irony in this. Big Ear had been dismantled because it was no longer efficient. Yet the most important thing it ever recorded could not be resolved by efficiency alone. It required time and patience, and perhaps luck. Years later, some would argue that if the WOW signal were ever confirmed as extraterrestrial, the dismantling of Big Ear would be remembered as a tragic misstep, a moment when humanity abandoned a listening post too soon. Others would argue that even then, the telescope had already served its purpose, that it had listened when it needed to, and that its legacy lay not in what it might have done, but in what it had already done. Both views contained truth. The instrument fell silent. The question did not. As new generations of researchers entered the field, they encountered the WOW signal not as a recent event, but as a historical artifact, something that had happened before they were born, preserved in scanned documents and retold stories. Yet it retained its power precisely because it was unresolved. Big Ear's absence forced SETI to evolve. New searches became more automated, more comprehensive, and more statistically rigorous. Wideband receivers scanned billions of channels. Algorithms replaced human eyes. Follow-up protocols were refined. The field learned from the limitations exposed by the WOW signal, but it could not escape its shadow. The dismantling of Big Ear marked the end of one chapter in the search for extraterrestrial intelligence. It also marked the beginning of another, one in which the question no longer belonged to a single telescope, a single signal, or a single night, but to a broader effort that spanned continents and generations. The signal had been fleeting. The silence that followed was enduring, and somewhere between the two, the human desire to listen remained unchanged. Chapter 5. Those who kept listening. When Big Ear went silent, the signal did not. It existed now in a different form, not as radio energy moving through space, but as an idea moving through people. Detached from the telescope that had captured it, the WOW signal became portable. It could be carried in books, lectures, scanned printouts, and conversations held late at night between scientists, engineers, and amateurs who refused to let the mystery settle quietly into obscurity. This was the phase that no funding agency planned for, the afterlife of an unresolved event. For some, the dismantling of Big Ear marked the end of the story. An anomaly had been recorded, investigated, and archived. The instrument was gone. The data had been reviewed. Science, they argued, could not afford to linger indefinitely on a single observation that refused to yield new information. Resources were limited. Questions were abundant. Attention had to move forward. But for others, the opposite was true. The fact that the signal could not be explained and had never been repeated made it more important, not less. It represented the exact class of phenomenon that the search for extraterrestrial intelligence was designed to notice, something rare, narrow, and unexpected, appearing briefly against a background of cosmic noise. And so, long after the original instrument was gone, people continued to listen. Among the first to take up that task independently was Robert Gray. Gray was not part of the original Ohio State team. He encountered the wow signal the way many did, through an article, a reference in a scientific magazine, a short description that hinted at something unresolved. But unlike most readers, he did not move on. He did not file it away as an interesting footnote or a curiosity from an earlier era. He wanted to see the data. He wanted to understand how the signal behaved, not as legend, but as measurement. And more importantly, he wanted to know whether it could be found again. Gray approached the problem without institutional backing or formal authority. He did not control a major observatory. He did not command dedicated telescope time. What he had instead was patience, technical competence, and a willingness to pursue a single question for years, without expectation of recognition or success. This made him unusual, and in a sense, well suited to the task. Gray began by immersing himself in the details of the wow signal. He studied everything that had been published about it, reconstructing the telescope's beam pattern, the timing of the event, and the precise region of sky from which the signal had originated. He examined the frequency range, the narrow bandwidth, and the constraints imposed by the two feed horns that had detected the signal only once. He treated the signal not as a story, but as a target. If it had been transmitted once, perhaps it would be transmitted again, not continuously, not predictably, but possibly. Using his own equipment, far more modest than Big Ear, Gray began observing the same region of sky. His early efforts were limited by sensitivity. A signal as strong as the original wow event might have been detectable, but anything weaker would be lost in the noise. He understood this limitation and accepted it. The goal was not certainty, but coverage. Still, he listened. Later, Gray gained access to larger facilities, including professional observatories willing to allocate limited time to the search. Each observation was planned carefully. Frequencies were selected based on the original detection. Observing windows were timed to match Earth's rotation relative to the signal's coordinates. Data was recorded, stored, and analyzed methodically. Years passed. Nothing appeared. This absence did not discourage Gray. Instead, it refined his thinking. The more he studied SETI strategy, the more he became convinced that one of its central assumptions might be flawed. Early SETI efforts often imagined extraterrestrial civilizations broadcasting continuously in all directions, a kind of omnidirectional beacon announcing their presence to the galaxy. But such a strategy would require enormous energy expenditure, far beyond what even an advanced civilization might choose to sustain indefinitely. Efficiency, Gray reasoned, would favor directionality. A civilization capable of interstellar transmission would likely focus its energy into narrow beams, aimed deliberately rather than broadcast indiscriminately. Such beams might sweep across the sky slowly, touching any given point only briefly. From the perspective of an observer on Earth, this would appear as a rare, transient signal, detectable only when alignment, timing, and chance coincided. Under that model, the wow signal did not need to repeat on human timescales to be real. It only needed to have happened once. This interpretation placed SETI in an uncomfortable position. It meant that non-detection could not be taken as evidence of absence. Silence could mean many things. It could mean there was nothing to hear, or it could mean the signal had passed and would not return for centuries, or it could mean Earth was simply not a priority target. The wow signal became a symbol of that ambiguity. As Gray continued his work, he encountered skepticism, not hostility, but distance. Professional astronomers respected the discipline of his approach, but many were reluctant to devote scarce resources to a single unresolved event from decades earlier. Telescope time was precious. New surveys promised broader returns. Careers depended on results that could be published, cited, and built upon. Science tends to move forward, not backward. Gray understood this. He did not argue that the wow signal deserved exclusive attention. What he argued, implicitly through his actions, was that some questions required persistence rather than novelty. If the signal represented a genuine transmission, it might never be rediscovered unless someone deliberately chose to look for it. And so, he kept looking. Beyond Gray, the signal took on a second life in the public imagination. Unlike many scientific anomalies, the wow signal was unusually accessible. It did not rely on complex equations or specialized knowledge to describe. It was not hidden behind classified data or proprietary algorithms. It had a name. It had a physical artifact. It had a moment of human reaction captured in ink, a piece of paper, a red circle, a word written in surprise. This simplicity made it powerful. It allowed non-specialists to engage with a real scientific mystery without distortion. There were no photographs of spacecraft, no eyewitness accounts, no dramatic claims, just data and an honest admission of uncertainty. This accessibility was both a gift and a burden. On one hand, it preserved the signal's credibility. It remained grounded in observation rather than speculation. On the other, it invited misinterpretation. Some treated it as evidence of extraterrestrial contact, ignoring the caution with which it had always been discussed by those closest to it. Scientists were careful to push back against this framing. The wow signal was not proof of aliens. It was proof of an unexplained signal. The distinction mattered. As SETI matured as a discipline, the signal became a reference point. New candidate detections were measured against it. Did they exhibit the same narrow bandwidth? Did they follow celestial motion rather than terrestrial interference? Did they avoid repetition patterns consistent with satellites or aircraft? Most did not. Those that came close eventually yielded explanations, instrumental artifacts, reflections, or human-made transmissions. The wow signal remained unique, not because it was dramatic, but because it had resisted explanation despite sustained attention. In the late 1990s and early 2000s, advances in digital signal processing transformed SETI. Distributed computing projects allowed enormous datasets to be analyzed collaboratively. New surveys scanned vast swaths of the radio spectrum with unprecedented speed. The search became broader, covering more of the sky and more frequencies than ever before. But it also became shallower. Individual targets received less sustained attention. The sky was sampled rather than studied deeply. In this environment, the wow signal stood apart, not because it was louder or clearer, but because it had been examined closely. Its mystery endured not due to neglect, but despite scrutiny. Occasionally, new hypotheses emerged. Some suggested the signal might have originated from a rare astrophysical phenomenon not yet fully understood. Others revisited the possibility of reflections from space debris or distant objects. Decades later, proposals involving hydrogen emissions from comets were raised and debated, supported by partial correlations and challenged by inconsistencies. Each hypothesis explained something. None explained everything, and none produced a repeatable demonstration. Through all of this, the signal endured not as proof, but as pressure. Pressure on assumptions, pressure on methodology, pressure on the idea that silence is the natural state of the universe. For those who kept listening, the wow signal became a reminder that discovery does not always arrive fully formed. Sometimes it arrives incomplete. Sometimes it leaves behind a question rather than an answer. And sometimes that question persists long enough to shape how an entire field thinks about its purpose. Robert Gray eventually acknowledged what he had always known. He might never find the signal again. And even if he did, proving its origin would remain extraordinarily difficult. But that did not diminish the value of the search. Because the act of listening, patient, disciplined, and honest, was itself the point. Long after Big Ear was gone, the wow signal continued to do its quiet work. It kept SETI humble, it kept speculation in check, and it reminded those who studied it that the universe does not owe us repetition, only opportunity. Chapter 6. What the silence leaves behind. Every search eventually confronts the same question. Not whether it will succeed, but whether it will be allowed to continue once success fails to arrive on schedule. By the time the wow signal had settled into its long afterlife, studied, debated, cited, and quietly carried forward, the search for extraterrestrial intelligence had already changed. New telescopes scanned wider fields. New algorithms processed more data than human eyes ever could. Listening became faster, broader, and more automated. But the fundamental condition remained unchanged. The universe did not answer on demand. The wow signal sat at the center of this realization, not as a breakthrough, but as a boundary. It marked the point at which listening became something more than a technical exercise. It became an act of patience, restraint, and humility, because nothing about the signal had resolved the question it raised. It had only clarified what the question was. The signal itself was small by astronomical standards, 72 seconds, a narrow slice of spectrum, a brief alignment between a fixed instrument and a distant point in the sky. It did not overwhelm the senses. It did not demand interpretation. It simply appeared. And then it did what the universe does most often. It stopped. What followed was not failure, but adjustment. Scientists learned, slowly and sometimes reluctantly, that SETI could not function like other fields. There would be no controlled experiments, no repeatable trials, no guarantee that effort would correlate with outcome. Listening was not the same as measuring, and silence was not the same as absence. This distinction shaped everything that came after. Over time, the wow signal became less important as an event and more important as a reference. It influenced how candidates were evaluated, how false positives were filtered, how follow-up protocols were designed. It taught researchers what a genuinely unusual signal looked like, not in theory, but in practice. It also taught them what restraint looked like. The signal had been neither dismissed nor declared definitive. It had been carried forward carefully, intact, without being forced into a narrative it could not support. This, more than the signal itself, became its lasting contribution. It demonstrated that science could live with unresolved data. As newer searches expanded across the sky, some hoped that a similar signal would appear again, validating the wow event retroactively. Others quietly suspected that it might remain singular, not because it was unique in the universe, but because coincidence plays a larger role in detection than most models are comfortable admitting. Alignment matters, timing matters, chance matters. A civilization transmitting intermittently, directionally, or indifferently would leave behind exactly the kind of trace the wow signal represented. A brief intersection between intent and detection, followed by nothing, not a message, a moment. This possibility unsettled people. It challenged the comforting idea that discovery arrives clearly labeled, repeatable, and self-verifying. It suggested instead that some truths might be glimpsed only once, without confirmation, and that recognizing them required a willingness to tolerate uncertainty. That tolerance was not universal. Funding agencies demanded outcomes. Institutions demanded efficiency. Public attention drifted toward more tangible discoveries. Exoplanets catalogued, spectra analyzed, atmospheres modeled. These were achievements that accumulated reliably, that rewarded persistence with measurable returns. SETI remained different. It asked a question whose answer might never come, and yet the question endured. Are we alone? It survived not because the wow signal proved anything, but because it demonstrated that the universe could still surprise us in ways that resisted immediate explanation. It reminded scientists that not everything important announces itself loudly or repeatedly. Some things whisper once and then wait. As decades passed, the signal's meaning shifted again, not in content, but in context. It became a historical artifact, studied by people who had grown up in a world where Big Ear no longer existed, where radio astronomy had become computationally dense and globally distributed. To them, the wow signal was not a recent mystery. It was a reminder of a time when listening required patience rather than processing power, when detection involved human attention rather than automated classification, when discovery arrived on paper rather than screens. This contrast mattered, because it revealed how much the search had changed and how much it had not. The modern search listens to more of the universe than ever before. It does so faster, with greater sensitivity, and with fewer assumptions about what a signal should look like. Algorithms scan billions of channels. Machine learning models classify anomalies. Follow-up observations can be initiated almost instantly. And still, the sky remains quiet. This quiet is not discouraging to those who understand it. It is instructive. It teaches that intelligence, if it exists elsewhere, does not owe us accessibility. That technological capability does not imply communicative intent. That the universe is under no obligation to reassure us of our significance. The wow signal did not contradict this. It embodied it. There is a temptation to ask whether the signal was wasted, whether it mattered that it could not be repeated, whether tearing down the instrument that detected it was a mistake. These questions assume that value is measured by resolution, but the history of science suggests otherwise. Some observations matter because they close debates. Others matter because they open them. The wow signal did the latter. It opened a conversation about how we listen, about what we expect to hear, about whether confirmation is always necessary to justify curiosity, and about whether the absence of answers should diminish the worth of asking. For SETI, these were not abstract concerns. They shaped methodology, funding arguments, and public perception. They influenced whether the search was framed as speculative indulgence or disciplined inquiry. The signal helped clarify that distinction. It showed that listening could be done rigorously, even when results were inconclusive. At its core, the wow signal forced a reckoning with scale. The scale of time in which civilizations may rise and fall before their signals intersect. The scale of space in which beams narrow and miss more than they strike. The scale of expectation in which human impatience confronts cosmic indifference. Once these scales are acknowledged, silence becomes less ominous. It becomes contextual. There is a quiet humility in accepting that the universe does not revolve around our readiness. That discovery may occur when we are unprepared to interpret it. That meaning may arrive without explanation. The wow signal asked for that humility. It did not demand belief. It demanded care. In the end, the most enduring impact of the signal may not lie in what it was, but in how it was treated. It was recorded faithfully. It was investigated thoroughly. It was discussed honestly. And when it refused to yield answers, it was left intact rather than distorted. This is not a failure of science. It is one of its highest disciplines. The search for extraterrestrial intelligence continues. It does so with better tools, broader coverage, and more refined assumptions. It listens not only for beacons, but for anomalies. Not only for repetition, but for structure. Not only for messages, but for intent. And somewhere within that expanded effort, the memory of the wow signal persists, not as proof, but as precedent. It reminds researchers that the universe is capable of producing signals that do not fit our expectations. That detection is sometimes an encounter rather than a dialogue. And that patience is not a passive state, but an active commitment to remain attentive in the absence of response. When Big Ear fell silent, the listening did not stop. It simply changed form. From a single instrument to a distributed effort, from paper to computation, from a moment to a mindset. The signal was fleeting. The silence that followed was long. But within that silence, something endured. The willingness to listen anyway. The willingness to wait. And the quiet understanding that the universe may speak rarely, but not meaninglessly. This is what the wow signal leaves behind. Not an answer, but a posture, a way of standing in the presence of the unknown without rushing to fill it. A reminder that some questions are worth asking even when they do not resolve, and that listening in its purest form is an act of respect for the universe and for our place within it. This was a quiet archive story, where the story ends, sleep begins,